that we had the following situation that we have this some triangulated category, then we defined notion of C structure. It's two subcategories with some properties. And we have intersection of these two categories. It's called heart of T structure. Okay, and the case which we are interested in is when D is equal D of x, which is by definition derived category of bounded complexes on sheaves on X is constructible homologies, where X is algebraic varieties, and we have perverse T structure. And its heart is category of perverse sheaves. So this is definition. So first I want to make several remarks. First of all, if you have this situation, then so how we model where we come idea of this situation, it says that if D is equal to some DAB, then it has natural C structure. And heart of this C structure is equal to A. This was how it was. So, and we would like, in principle, if you have any triangulated category, you have C structure, you have its heart, we would like to think about this as special case of this. So we would like somehow, because here we can understand all the properties very naturally, and here it's more difficult. Okay, so then, since notion of triangulated category is not very good, then it doesn't always happen. So if you have such thing, for example, in this case, you have natural morphism D of A into D AB. Well, in fact, it's enough that you have complex. If you have complex of A, you can assign to it object in DAB. In general, so the T structure, it's not clear whether it's possible to do it. Probably it is not. Again, if you work in correct language of omega categories, it's always possible. But here it is not. But there are some tricks that, for instance, in this case, it is correct. So claim, I will say, claim, first there exists a morphism, a functor, complexes of perverse sheaves into D of x. Second, that natural factor, that second that it maps acyclic into acyclic, quasi-isomorphism into isomorphism. Quasi-isomorphism into isomorphisms. In particular, defines functor d of A into d of perverse into d of x. And third is much more difficult statement that in fact this is equivalence of categories. This functor f is an equivalence. Okay, just let me explain the status of all these things. So this theorem is, I don't know, maybe we'll discuss it. This result by Bernstein, and this is difficult. And this is relatively easy. So the idea is that d of x is not just an integrated category, it is in fact derived category of something. And derived category of something are better than general integrated categories. You can use it, but as far as there was no way to formalize it. So how each time you can do this. So there is some standard way. It's pretty. So probably I will discuss at some moment. So these statements are easy, and this statement is difficult. For instance, these statements, if you instead of this perversity you consider, for instance, standard perversity, then of course these statements are obvious, and this is not correct. So this is much more subtle and really interesting question. These are so once more, non-triviality of these claims is related only with the fact that notion of triviality category is not very correct notion. Okay, so this one thing. Yes, so the idea that we should always, when we're working with perverse sheaves and so on, not with absolute triangulated categories, we should always think that if you have, for instance, complex of perverse sheaves, and it gives you element in the derived category. So, okay, so so next thing what I want to describe today is classification of irreducible perverse sheaves. And I want to show that this thing in itself gives some highly non-trivial corollaries. So in order to classify this, I just list some properties of perverse sheaves. So first is that perverse sheaf, every object has finite length. Finite length. Second, maybe I will write this later. So first thing which we prove first is that how it behaves with respect to the duality. D of D more or equal to 0 is equal D less or equal to 0. D of D less or equal to 0 is equal to D more or equal to 0. So this T structure is invariant with respect to Bezier duality. In particular, D of perverse is equal to perverse. So it means that Bezier duality induces duality on abelian category of perverse sheaves. So this already shows that this is something much better than constructible sheaves where you don't have this property. Okay, and Now I want to outline other properties of this. Next thing is that I want to explain that these two conditions are essentially equivalent, or literally equivalent. That the idea is that I will not formulate. Okay. So the idea is that so the following. So claim so this category d of x is finite bounded with respect to perverse T-structure. So what does it mean? This means that we have so this T-structure defines as cohomological functors hi into perverse. So how we define it? So h naught of f is equal to tau less or equal to 0 of tau more equal to 0 of f. So if you have any f, you consider its truncation more equal to 0 than truncation less or equal to 0, and you'll get something which has only, which will be perverse. And then you get by shift. And bounded means that for any f, only for finite number of i's, hi of f is not equal to 0. So maybe I should denote this hip. It's perverse things. Okay, so this follows, this is easy fact, namely this is true by definition with respect to constructible perversity, and then we see that constructible perversity and perverse perversity differ by small amount, bounded by just dimension of our space X.
Does T of X denote a bounded derived category?
Yes, I always work only with bounded derived categories, because it's very difficult to work with unbounded. Yes.
The truncation here is the left adjoint of the inclusion of the smaller equal to 0 inside.
Yes, sure. No, this is general things. Yes. So the moment you have T-structure, you have truncation left and right, which I described some left or some adjoint functors of inclusions. Okay, so what does it mean? This means that so corollary every f for this particular T-structure is glued from objects T to the IP, finite number of objects T to the IP, where Pi are perverse sheaves. Okay, so you have any objects, only finite number of things not equal to 0. This means that if you truncate f, so this means that f truncation more equal to minus n will be just equal to f, and then truncation less or equal n of truncation more equal minus n of f is also equal to f. So you can, you know that all cohomologies outside the finite region are equal to 0, and then you just glue f from corresponding cohomologies Okay, so hence this implies that these two statements are equivalent, because if you have, if perverse is invariant with respect to this duality, so any f you can write down as finite glued from finite number of perverse. You apply duality, you get no. So any element in D plus, okay, if f is in D plus, D or equal to 0 just means that f is glued from T to the IP, where I are positive. This is just equivalent statement. So if you apply duality, then df will be glued from T to the minus IP, minus IF. Okay, so then df is glued from T minus I of dp. These are perverse, and this is, so hence it lies in D less or equal to 0. And conversely. Okay, so we often will use the fact that any f is glued from its cohomologies. Cohomologies are perverse cohomologies. That's important. Okay, so now I want to describe some geometric properties which we will use all the time, which are related to this standard triangle. So if you have Z, X, and U, where Z is closed and U is open. So then we have, so this I will denote by J, and this I will denote by I. So we have collection of functors. I star is equal I shake from D of Z into D of X. I star I shake from T of X to T of Z. Also J star is equal to J shake from D of X to D of U, and J star and J shake from T of U to T of X. And so we have different properties. For instance, this is equal to this is equal to this is just restriction. This direct image, which is the same as direct image with proper support. So and I want to list some properties of these factors with respect to T filtrations. For this, let me just say, so suppose I have two triangulate categories, D and D prime, and I have exact functor. And suppose here I have some T structure, D less or equal to 0, and here D prime less or equal to 0. So then, just by analogy with what we have, so let's just define. So F is left exact, T left exact, T left exact. So functor F, you assume that it's exact. It means that it maps exact triangles into exact triangles. So most of functors which we consider are of this type. But we would like to understand how they behave on hard. So T is left exact means that F of T more equal to 0 lies in D more equal to 0.
Just prime, right?
D prime, yes. So you can say that it's left exact or it is right moving. In particular, this would imply that if you consider H not F, then it maps perverse heart of T AD into AD prime is left exact. And similarly, we say that we say F is right exact, or the same left moving if f of d less or equal to 0 lies than d prime less or equal to 0.
I'm sorry.
Yes.
What is right moving?
The same as left exact.
The same as T left exact. And does this imply that H0F is left exact or equivalent?
Yes. So it's easy exercise to show that if f is right moving, that h naught of f is left exact functor.
Other direction is false.
Hmm?
Other direction is false.
Other direction is false. We discussed that if you have any factor and you move it, then so the idea is that it's very easy to construct functors such that this will be identically 0. If you take more or less any factor and then move it, just multiply by t to the I, then this will be automatically, just by finiteness, h naught will be just identically 0. So we discuss it. So the idea is that we use the same, we have an analogy that we think about this T structure as if it is this kind of category, and then it becomes just standard definitions. Okay, and so what I want to formulate here is the following properties property about exactness of these functors in this situation. So we consider perverse T structure, so then superposition. So functors I star and I shriek are exact, P exact or T exact. So P exact means exact with respect to T structure, perverse T structure. Similarly, functors J star, so this is the same functor, sig are exact. Now functor J star is left exact or right moving, and J shriek is right exact.
Could we please move from this part?
Yes. Okay, so let me. Okay, I will write it. So J star is left exact. J shriek is right exact. Now, only one of these statements should be proven because duality just maps one of them to another. So, so one second. Suppose J is affine compating. Affine means that preimage of affine set is affine. So then these functors are exact. J Schlick are exact. Okay, and now this next proposition about functor I, functors which are related to I. So proposition first that I Schlick is left exact, and I star is right exact. So I have written all these things because we are going to use them, and I explained already on Friday, on Thursday, and I want to explain once more. So how to prove these properties. So the idea is that since our definition of perverse thing was sufficiently complicated, so the proof will be some tedious checking. The correct question is how to see that this should be correct. And this you immediately see from D models. So perverse sheaves appeared from D model picture. In D model picture, all these properties are obvious because all these functors, essentially, for instance, this functor is just direct image. So for affine embedding, it is exact. For other embeddings, it is left exact, and so on. So, and for the claim is that D models is the case of D models is sufficiently generic case. It's clear that everything which is any general statement which is correct in this things should be correct in general. But if you want to prove it, so you just prove it. And so, as I explained, the essential lemma which you use, which gives all the. So what you want to show is, for instance, you want to show that if J star is affine, so this is most interesting, then it maps perverse sheaves into perverse sheaves. This means exactness. So how we check it? Perverse sheaves means that some relation, some conditional fibers on Stokes points. So how you check it? So you check it using the following standard lemma, that if X is affine algebraic variety of dimension n, and L is local system on X, then homology of XL is equal to 0 for I more than L. So in principle, as a real, as a topological space, it has dimension 2n. So in principle, you could expect homologies up to dimension 2n. But the claim is for affine, it's always bounded by n. And from this, you deduce this property by just computing, estimating fiber of direct image at all points. And from this, you deduce all the other properties. So this is some. So I explained why it should be true, and I think that it's better. Definitely, I'm not going to give detailed thing. Again, because our formal definition of perverse sheaves is pretty complicated, this condition and so on. So from this induce these statements, it requires just some checking. Okay, so next thing which I want to. Okay, so now I want to explain some. Important thing is the reason So this perverse notion of perverse sheaves provides some important construction. So how it's called? Perverse extension. So this is very important construction. Suppose we have U and X, U is open. So let's consider first U is case 1. U in X is a final braiding. Now, so let P be some perverse sheaf on U. That's what we can do. We can consider J star of P. And we consider J shriek of P. And we have canonical morphism. J shriek of P is mapped into J star of P. Now, since U is affine embedding, these are perverse sheaves. So now, so both these sheaves, when you stick them to U, they will be just P. And this morphism will be identity. But themselves, they are not P. So now what you can do, you can produce something from this thing. You can produce, in fact, several things. You can consider co-kernel of this morphism. You can consider kernel of this morphism. Or, the most important, you can consider image. So for this, there's even special notation. J shriek star of P, by definition, is equal image of J shriek of P in J star of P. Okay, and so the claim is that this defines some very useful construction. So the claim is that if you start with perverse sheaves on U, then the claim is that you can canonically, in some factorial way, extend it to some perverse sheaf on X. So of course you have this extension, but they somehow are not symmetric, not correct. And this extension is, we'll see many times, it's somehow much more very important thing. Once more, you cannot define this thing for arbitrary complex of constructible sheaves, only for perverse things. And we'll see that very often, we'll see a lot. This construction is used in the following way: that you have some thing here, you first check that it's perverse. It might require some work, but then you have canonical extension, and this extension is usually highly non-trivial and gives you some information which you cannot really get in any other way. Okay, so let's study some properties of this thing. So claim. So suppose P is irreducible. Simple. So then J shriek, J star, or J star shriek of P is also simple. Simple. Okay, so how to see it? Simple. Simple, irreducible, that's synonym. Okay, so how to see it? So suppose it is not simple. So proof. It is not simple. So it means that you have some exact sequence of the following type: F, J, P, H, where these are perverse sheaves. And both of them are not equal to 0. Now, let's say stick this simple sequence of sheaves to U. Since this is irreducible, this means that one of them will stick to 0 on U. Okay, suppose that F is stick to 0. So this means that F lies on the support of F. F lies in Z, which is X minus U. But the idea is that our we have embedding J shake star embeds into J star P. So hence we get so this is also embedding. You get a non-trivial morphism from here to here, but this is impossible because of base change. So if support of F lies outside of U, just by adjunction, any morphism from F here is equal to 0. So similarly, so if support of H lies in Z, then you use the fact that this is a quotient of J shake of P. And then the same consideration shows that it's, yes?
Why is this morphism non-trivial? Oh, it's composition of embeddings.
Composition of two embeddings, two non-zero embeddings. Composition of two embeddings. So this is an embedding. Okay, so this is an embedding, and if it is trivial, this means that F is equal to 0. You can argue this way. Okay, so from here we see, not only from here, you need one more thing. So lemma, which, so let X be smooth with dimension n. Then F is perverse local on X. So this means that F is equal local system shifted by n. So I have local system on X and shifted by n. So it will be perverse if X is smooth. So then any submodule, perverse submodule, G in F has the same shape. So it means that I have just submodule n, sublocal system n and L, and G is equal n shifted by n. So if on smooth things, if you consider just if you consider perverse sheaf is just locally constant, then classification of its submodels is just classification of submodels of this local system. And the idea that if you have local systems and so N is again local subsystem in L. Okay, so
So just a second. L is really a sheaf, usual sheaf,
moreover, not only sheaf, it is local system.
local system. When you shift it by n, it turns out that it's perverse. That's the
Yes.
assumption
No, this is always correct.
because the dimensions condition is
Yes,
automatically
because
set.
it is smooth. No.
I didn't know this assumption. Okay.
No. Otherwise, it will not be true. So it is on smooth. So first thing is that if you have X smooth, then being local perverse means exactly being locally constant and perverse exactly means that it's local system shifted by N. Yes.
It's if and only if, yes? It's if and only if.
Yes. This if and only if. So non-trivial statement. So this is trivial statement because just write down what's conditional perversity. Conditional perversity is that all fibers are.
There is only one
Okay.
stratum here.
Yes, there's only one
There's
stratum.
nothing to
Yes. So non-trivial statement is that any perverse subsheaf of this, which might be in principle not locally constant. The claim is that it has to be locally constant. Yes.
Don't you need to add the Irreducible of this to get the perverse sheaf itself? Because this is, you need to take,
So
because it's not really, it's the local system shifted by n plus the what's Irreducible.
No, you don't understand something.
Yes.
No. The idea that condition for perverse sheaf is there are two conditions for fibers and co-fibers. So for fibers, if you have local systems, and for fibers, it exactly means that all fibers will be concentrated in degree, so it's respectively minus n. Then when you come to with your dual, it will be, you should replace L by dual local system, slightly twisted, and put it in corresponding dimension, and then it automatically will be again correct condition. Okay, so this is easy and useful just to understand. Okay, this is easy, but as always, all these questions with normalization, I always hate this somehow. I remember everything up to some normalization, and then if I should do something, then I should just check again all normalizations. Okay, so it's useful to check it. But this is already non-trivial statement, so I think it's good exercise. Any perverse subsheaf of this will automatically be a local system. So why it is non-trivial? Because for constructible sheaves it's not true. If you see the different different structure, different perversity, it will be not correct. So it really requires something. Okay, so then let me give you classification. Of perverse sheaves. Perverse, irreducible, simple perverse sheaves. So classification is the following. Suppose I have X, I want to classify all irreducible perverse sheaves of X. Let's do the following. Let's choose in X, choose some S is smooth, locally closed separated. And it will be in fact also irreducible. Smooth, irreducible of dimension some dimension L. Let L be an irreducible local system on S. So then what I can do, I can consider S shifted by N will be perverse sheaf on S irreducible. Yes. Yes. S. Yes. Okay. Let me write it here. Anyway. So once more.
Doesn't being the entire.
Okay. So I give some construction of simple perverse sheaves, simple reducible. So construction. So given X break, right? So pick S is irreducible, smooth, subvariated of some dimension L. Pick L on S to be L. I'm not sure that L. Usually I denote E. Let's to be a reducible local system. On S. On E on S to be a reducible local system on S. Yes. So I consider J is an embedding S2 X. Then consider S L is perverse sheaf. S E, excuse me, L is perverse sheaf on S. And now I consider J star sheaf of this perverse sheaf. So this is perverse sheaf which is irreducible, simple.
S is locally closed.
S is locally closed.
Okay, so it's an enclosure.
Yes.
We only defined the Schlick style for the case of affine or open embeddings. If you have locally open, it's still fine.
Okay. So let's. No, I just forgot. I said that let's consider first case of affine embedding, but now let's consider case of non-affine embedding. So first of all, one can work only with affine embeddings, but it's just I want to just digression so let J U X be open. So I want to, in this case, I also want to define J chic perverse of U into perverse of X. In this case, it's also defined. Namely, if you consider J star of, you start with some F in P perverse sheaf on U. So suppose P is perverse on U. Then J star of P, it will be not perverse, but it will be, all its cohomologies will be in degrees 0, 1, and so on, positive degrees. J sig of P will be so in positive degrees. This will be in negative degrees, not in degrees less or equal to 0. So you have, just let's think about this complex. You have morphism of complex less or equal to 0, complex which is more equal to 0. I claim that in this case, you can well define what is an image of this thing in perverse in category. You can define it formally, you just consider H naught of this, image of H naught of this into H naught of this. So you can give formal definition, but the formal definition I can give for any morphism, it will be just meaningless. In this case, because it is, so to say, here it differs from perverse sheaf just by something in negative dimension, and this differs from perverse sheaf by something in positive dimension. It's just the image is well defined. So to give formal definition, no problem. But I'm saying that this formal definition makes sense in this case. Yes.
When you say positive degrees, you mean again it belongs to D grade or
negative.
Yes. Yes, exactly. Yes. It belongs to D more or equal to 0. And this belongs to D less or equal to 0. So I claim that if you have morphism of some object of degree less or equal to 0 into some object which of degree more or equal to 0, then the image is well defined as a perverse object. Okay, so hence for any open embedding you can define this. So this defines you this functor, which I described here. And if you have locally closed embeddings, then you consider this composition of open embedding, closed embedding. For closed embedding, it's just J sheik, which is equal to J star, I sheik, which is equal, I low sheik, which is equal to I low star, and for open embedding, you have this. So hence, in any case, if you have locally closed embedding, you have this functor, perverse of S into perverse of X. And we have seen that it maps irreducible into irreducible. Okay, so hence starting from, so I will denote this L of S E. So if I have a irreducible subvariety and local system, irreducible smooth subvariety, and local system of this subvariety, I will construct some irreducible perverse sheaf. So the claim is that any irreducible perverse sheaf has this shape, and some of them are isomorphic, which I will describe in a moment. Yes?
When you say that the image here of this map is defining perverse sheaf, you mean you truncate the first one above, you truncate the second one below, you take this map and the image of this?
Yes, so, okay, so just, so once more, I can, if you have any morphism of any two complexes, you can formally take H naught of this, H naught of this, and take image. This will be well defined, but completely meaningless. Just what I'm saying is that in this particular case, it is meaningful object, but
I think maybe the way to explain this is that because of the direction of the arrow here, this map factors through the truncation. Yes, if you have an embedding between something which is like this and something which is like this, then the map factors through the truncation into the H0 here,
yes,
and through the H0 here. So if you can restrict it inwards, just H0 to H0, and then it is obvious what the image is.
okay, so once more, it's very easy to give formal definition, but at the same time to explain that in this particular case, this formal definition also makes some informal sense. It's meaningful object. Okay, so this gives us construction, and so the claim is, so claim any simple perverse sheaf L, okay, is isomorphic to some L of S E. And second, you can also reconstruct, this will be automatically, that L of S E is isomorphic to L of S prime E prime. if and only if S closure of S is equal to closure of S prime, and exists an open dense in S intersection S prime, dense U, such that E restricted to U is isomorphic to E prime restricted to U. So in other words, the only way when two such things can coincide is that so if you have some S, you can delete some closed subset of S, you can shrink S a little bit and restrict E to this shrink subset. The claim is that the result, this L of SE will not change. And that's the only way how it doesn't change. And the proof is in fact pretty simple. So okay, this right here. So let F be reducible. That's proof. So consider support of F. So it will be some variety. Choose S to be open, smooth, smooth part of one of components. Then consider J shake of F. So again, if you shrink F, then this will be a perverse local constant, perverse local system on S. So it will be perverse. If it's not local system, you just shrink S a little bit so to make it locally constant. And then what you have, then you have a morphism. So in what direction? Local system. So let's denote this local system by E. No. Choose and a simple and irreducible, I think, quotient E of this local system. So then the claim is that in this case you will get a non-trivial morphism, just quotient or sub. Okay, so the claim is that you. Okay, so let's consider. So let's denote this H. So you have home H, home J, shake of H into F is not equal to 0. So then, so not quotient, subsystem. System. So then this implies that by adjunction this give is not equal to 0. Then so this implies that this area of SE has non-zero morphism into F. And hence F is isomorphic to L of SE. Okay, so once more, the construction is so starting from F, I would like to construct S and E. So how I construct S and E, I look at the support of F. In principle, it can have several components. It will turn out that it has just one component, but we don't know yet. Take one of these components, take sufficiently small open part of it, which is restrict F to this component, you'll get some local system. Again, this local system a priori maybe is not irreducible, but in fact it will be irreducible. So we choose some irreducible sub in it, E. So this gives me S and E. And then by just by construction you have some non-trivial morphism from L of SE into F. Since F is irreducible, this means that it's nice morphism. And from this construction, you immediately see also this. So you see that F, for instance, has its supporting factors irreducible, and if you constructed S, no, if you just you can just say that if you take L of SE and apply the same algorithm, you'll recover S up to shrinking and E up to restriction. Okay, so both, so something the claim is just obvious after this things. Okay, so now it's a good time for a break because I almost finished the first part.